And every day keeps fascinating me more and more.
She's the professor of Human Spaceflight Technology.
And I'll never forget one of my first lectures, and he started explaining how it was when he was in space. That was astronaut and Professor Ernst Messerschmidt. Big focus was on life support systems. And that's what fascinated me and where I decided that's the path I want to take.
You already talked about microalgae on the ISS.
It's amazing to know that the thing you have built with your own hands, it's up there. We learn about developing technologies that allow us to live in a world that it's not made for us. Mars is definitely not the place for humans to live in. And if we are able to think to that limit, how do we make the impossible possible? That brings us to come with ideas or with potential technologies that can also be used here on Earth.
Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Hello everyone, and welcome back to another episode of On Air, Actually Rocket Science, the official student podcast of the Student Council of Aerospace and Geodesy. We are today's host. I'm Lily.
I'm Mikkel, hello.
And today we are welcoming a very special guest. She's the Professor of Human Spaceflight Technology. Welcome, Professor Detrell.
Thank you. Hello everyone.
Okay, first of all, we start with a small warm-up. This or that questions. I would say something like apple or banana, and then you have to choose one of them. The first one would be moon landing or Mars mission.
Oh, that's a hard one. Let's start with moon.
Okay, living on the ISS or a Mars colony?
Let's think a little bit more in the future now, so Mars colony. Okay.
The next one would be private spaceflight or governmental spaceflight.
Oh, can I have both, please?
Sure.
Okay, biological or mechanical life support systems?
Biological.
Star Wars or Star Trek?
Star Wars.
Okay, and very important, Stuttgart or Munich?
Munich.
Okay, now we can
don't
start.
tell the people in
Yeah.
Stuttgart.
Now we can start the
Now
podcast.
we can start with the podcast. So let's take it back to the very beginning of your career. You studied aerospace in Barcelona. And what was your inspiration behind choosing this major?
I have to be honest, I didn't want to be an astronaut as a child. I didn't look up to space and was inspired. I actually started aerospace engineering because I wanted to be an engineer. It was aeronautics, at the moment, my goal, but it could have been anything else. As a child, I was curious. I liked solving puzzles, understanding how things work, improving things. So I had clear in my mind, I want to be an engineer. I had the opportunity to work at school in a project related to airplanes. When I was 16, 17 at school, we were offered the opportunity with two colleagues to work in a project to explain why do airplanes fly. At a very basic level, we were at school. And to actually build a couple of airplanes with different types of wing and make them fly and explain why one was flying faster, the other one farther away. So that brought me to say, okay, aeronautics is actually a cool field from engineering. So I started studying aerospace engineering in Barcelona. And while I was already in the studies, I discovered space, first looking at satellites and rockets, and at some point at human spaceflight. So I found my path over the way of my studies. Yeah, it was not a decision. I wanted to do that for my entire life. I step by step found my way up to here now.
But what was like a event that inspired you to specialize in life support systems?
That was in Stuttgart. I had the opportunity to go there for one semester as exchange student, as Erasmus student. And I'll never forget one of my first lectures. When I was sitting there, I didn't know who the professor was. And he started explaining how it was when he was in space. That was astronaut and Professor Ernst Messerschmidt. And I learned after what he was doing in terms of research at the University of Stuttgart. And it was big focus was on life support systems. And that's what fascinated me and where I decided that's the path I want to take. I decided to stay there for my PhD. And since then, been working more or less on this field. And every day keeps fascinating me more and more. So it's still growing in me, the life support system field.
Okay, speaking of your experience in Stuttgart, we heard you were leading a research group there. What was the most significant project you had?
So it's not a project that I started, but I took over with the years, and I was very involved in the last 4 or 5 years. And that was an experiment on the ISS, the Photobioreactor. We had been working in Stuttgart for many years on how to design a system to cultivate algae in space. We're mostly engineers, so even if I talk about algae, don't imagine a team of biologists looking into details into the cells, but rather, what technology do we need so they can grow in space? And after many years, we had the opportunity to actually design an experiment for the ISS. And the team lead that moment left. I was the most experienced engineer left in the group. And I took over the lead of this project and finalized it, brought up to space. Well, not myself, but did all the steps required to finally bring it to space. And funny story, well, not funny, but interesting story is the experiment was meant to work for 6 months. We wanted to show that for long term, such an experiment can work. It failed after 2 weeks.
Oh.
Not our fault, but there were some technical problems with the experiment that unfortunately happens quite often with experiments in space, and you cannot repair it as easily as you do here on Earth. So it was not a fully successful experiment, but of course for us as an institute, as a university, we learn a lot. I got a lot of experience on how to design an experiment for space, what are the requirements, the constraints, who to talk to finally get something like that done. So I bring that experience now with me in a positive sense, even if the experiment did not go as planned. And I hope that's also then going to happen here, that in the next years we'll also see some algae from Munich going up to the station.
How was the feeling when you knew that there's an experiment that you work on or are the lead on is on the ISS?
It's amazing. It's amazing to know that the thing you have built with your own hands, it's up there. I did not build the entire experiment myself, but I was part of the team building some of the parts of the experiment. And the moment when you're in the lab building it and you know, oh, that's going to be up, of course, it's a very exciting moment. I also had the opportunity to go to the US to see the launch live. And that was amazing. I already had seen rockets starting before from Kennedy Space Center. But knowing that the things you have built are up there going up, it makes you more nervous to really like, oh, let's hope that it goes all the way up the way it's supposed to be. And you're more nervous than watching a normal flight. And the day it was installed, we had a live video that we could see how the astronaut was mounting the experiment. And it was really exciting. On the other hand, the day I got the call the experiment was not working, that was the hardest day work-wise of my life. I was on holidays back home in Spain, and I got a call on a Sunday afternoon. And that was harsh. So it's a lot of ups and downs in research. Things like this happen. Sometimes you get very excited as at the moment your experiment goes up to the station. But it also comes with, sometimes, not so good news. So it's a roller coaster.
And how is it like to work with space agencies like ESA? How do they work? How does the communication between the university and those agencies look like?
I would say it really depends on the person, but it's a very interesting discussions because they are used to work in different ways as we do at our university, or we work differently than those agencies, and we can learn a lot. They have been on the process from this ISS experiment, but in general with other projects that we had together with DLR or ESA, they are very supportive and they always are very enthusiastic about the work we do. So we find a lot of support from their side towards the activities that we're doing. So it's always been a very nice work. Of course, you have to get used of bureaucracy being different than what we're used to university. Especially when things have to fly to space, it's quite strict, the regulations there are and all the documents we have to provide. The university, sometimes we tend to do things in a more quicker way and document more or less. That's not always the case when you want to actually fly things to space. There are many rules that you have to follow. So it can be a little bit stressful in that sense. But we always got very positive feedback. Everyone was very excited about our experiment. And it's nice that you see that others are also excited about your experiment, not just you, because of course you are, yes. But seeing that others also are, it's just amazing.
Yeah. So the experiment worked for 2 weeks. Did you get any key findings on the 2 weeks that the experiment worked?
Since it only worked for 2 weeks and we had some troubles already technically those 2 weeks, we cannot make any strong statements on our experiment. We demonstrated that the algae can grow in a system such as the one we designed, because the failure was not, the algae did not die, it was a technical failure. So the housing for the algae was right, but we cannot extract any high level science information. The algae seem to be growing better than here on Earth, which is something to be expected. The microalgae are living organisms that are more or less floating in a liquid. Here on Earth, because we have gravity, they go down and sediment, so they don't grow that good because of that fact. We already expect the algae not to sediment in space, so we assume that the mixture, the entire process that happens around them would be better. And we saw that a little bit on those first 2 weeks. But of course, we needed more weeks of experiment to be able to make strong statements about the results.
Okay, so for all the listeners we switch a bit the topics now. For all the listeners who are not 100% into the topic of life support systems, could we go into the basics and maybe you give us a short and brief explanation about the requirements of life support systems like oxygen, like water, power supply, waste management?
Yeah. So the life support system is the system that makes sure that astronauts can survive up in space, out from our planet Earth. Our planet Earth has a life support system. We breathe, we eat, we drink. It, in one way or another, takes care of the waste that we produce. We can argue if better or worse and how we deal with that, but we have our own life support system. Inside the station, we have to create that. And for that, there are certain tasks that need to be fulfilled. So from one side, we have atmosphere management. We all breathe. We need oxygen, a certain amount of oxygen, so our body can actually take the oxygen around us. We have to make sure that this atmosphere doesn't have too much carbon dioxide. We as humans are producers of carbon dioxide. And here on Earth, we can open the windows and get fresh air. That's okay. On the station, you cannot. So we need other means of making sure that the CO2, this carbon dioxide, doesn't accumulate on the station, because it would really be toxic for the humans. From the atmosphere, we also have temperature and humidity, so there are some parameters to be controlled. Beyond the atmosphere management, we have the water management. We need to make sure we provide enough water for drinking purposes. We as humans take, the doctor always says, 2 liters of water per day. We take a little bit more because included in our food, there's probably another liter at least, or yeah. We could say that we need per person on average about 3.5 liters per day. And we need water for drinking, but we could also add a little bit water for hygiene purposes. It's not much what they get today on the ISS, but a certain amount for hygiene is required for everyone. Beyond that, we need to eat. So food is the next big management system that we require. Food needs to be provided to make sure we get enough energy, the energy that our body consumes. So it has to be a certain balance and enough energy diet that we would require. And the food has to come from somewhere, either brought from Earth or produced on board the station or the base. And the last one is waste disposal. That counts for all the types of waste that we humans produce in a liquid or solid phase. It has to be at least collected and stored in one way or another, and ideally further processed so we can recycle it. So those are the 4 big management groups that we have on a life support system. Now, today, we are at the stage where we are able to recycle partially. The International Space Stations, where we have astronauts now for over 24 years in a continuous way, there, it's possible to recover about 42% of the oxygen from the carbon dioxide that the astronauts produce. So less than 50% of the air, we could say air as a general concept, is being recycled. From the water, it's about 90%. So a big part of the water that the astronauts use, it's reused, cleaned and reused. Also coming from the urine from the astronauts. So it's not just the water from the condensate or sweating from the astronauts, but actually urine is also being recycled. And there are many experiments currently taking place already for a year or 2, trying to increase that more. Because in water, it's something we can really increase up to maybe not 100%, but close. Food is the interesting part because we are currently producing everything on Earth and bringing it up. So that's one big field of research where there's many people working around the world, looking at microalgae as we are here, but also at higher plants. Could we grow tomatoes on Mars? So there are many topics on that direction on how we could change that on the future if we want to go farther away from Earth. How could we be able to produce food in situ wherever we put our station?
So you already said we can't recycle 100% at the moment. What do you think, how far are we away from like a closed loop cycle?
Completely close, very far away. All systems have losses and will not avoid that. So having a system that it's completely 100% closed, that makes sure that we get everything that we humans required absolutely there, it's very hard. Because even if we are able to produce certain plants or certain food, we have a lot of variety here on Earth. So there might be things that we might be missing if we imagine a small station with food production on its own. So there might be small things that we're not able to make sure we provide right now, not because it's not technically possible to produce one substance, but because we humans are very complex. So it's very hard to make sure that we long-term will have no bad impact because of the food that we eat currently being produced in our station. So it's a very complex topic. So being sure we can be fully independent and have nothing to do with Earth resources at all, I think we're far away. But it is true that we can close and close more the cycles. With the water was a good example, but in general with the air as well and with the food, that we only need very small still supplements for the well-being of the humans.
Okay, so for a long distance space flight, like maybe in some years to Mars, we can't have those supplements from Earth being taken to the space station. So what would be the maximum duration of such a space mission right now with the current state of technology? Is it 3 years or more? How much could...
That's a hard question to answer because there are many factors in play.
Mm-hmm.
And one is not what I do, but of course something I'm very aware of, and that's radiation. So one of the biggest issues about sending humans to space, it's the exposure to space radiation. We have many years of experience of having astronauts on the ISS where the radiation is slightly higher than here on the surface. But as long as we go farther away from Earth and we're not protected anymore from the Earth magnetosphere, we are exposed to space radiation fully. And that's one of the limiting factors. It's not that much about the resources I can take with me or how I can recycle them, but rather the risk that it poses to the humans. I don't dare to say a duration which could be a limit for that. But there are many discussions on how long a Mars mission should be. There are 2 scenarios being studied. A scenario that would allow to have a short stay on the Martian surface and a scenario that would allow or would include a long stay on Mars. And even for the long stay, we're talking about 900 days. And we already say that has quite a high risk for the humans in terms of radiation. So that could be until we can find a better way to protect the humans from radiation or travel faster to far destinations. That sounds quite of a limit where we currently are very aware of a high risk for the humans.
So we already talked a little bit about the current state of life support systems. Do you have any favorite innovation or technologies of the past 5, let's say 2 to 10 years?
For life support systems specifically. I've been very fascinated by all the things that are being investigated in general on the biology side. One of the quick questions you asked me at the beginning was biological or physical-chemical life support system, and I immediately said biological. I think it's amazing all the things that have been investigated in that sense. Starting from, of course, our own research on microalgae, but there are also many groups in Europe and worldwide looking into that. And there's one very good example. It's a long-term project from the European Space Agency with partners all over Europe. That's called Melissa. And they use biology in a very precise way. They can really control their biology systems by changing the light, like you would change a mechanical system. Like I want to produce more oxygen. I know how much light I have to increase to get a certain amount of oxygen. And they have been able to model and verify those models with their systems. Also on the space station, they also had an experiment with cyanobacteria, with kind of microalgae on the ISS. And they put their simulation and their data from biology, and it matched perfectly. And for me, that's amazing. I'm an engineer, and I'm always a little bit scared of biology. Like, oh, I don't know. I don't understand it fully. I don't know how it will react. So for me, that's something amazing that has happened these last years, that they know exactly how this will behave and how to control and manage it.
You already talked about microalgae. You worked a lot about it in the past years. Could you maybe explain us how do they work?
So microalgae, they grow pretty much everywhere. We quite often hear about places where microalgae grow where we don't want them to grow, these algae blooms that happen. We see big pictures of lakes with a lot of algae on it. So algae growing by itself, it's not the issue. Algae grow if they have enough nutrients, if they have the right temperature, the right conditions, they do. But they might do it in a not controlled way. For a space station, we need the algae to grow exactly as we want them to be. We want them to continuously produce the amount of oxygen that our astronauts require. So one of the main goals of the cultivation of microalgae is the oxygen production. At the same time, of course, they use the CO2 that we produce, and it can be eaten. We call it biomass, that is so the algae growing. We can actually eat that. And the big challenge compared to how algae grow on Earth is that we want them in a closed environment that we can control very well and that it works stable for long periods of time. Experiments on the lab with algae, they usually last for other purposes. They usually last for a month, 2 months. The life support system, it has to work for 10 years. So we're talking about a completely different order of magnitude. And we have to make sure that that's possible and that we know how to deal with it. So we need to make sure that we have the reactors, let's say the housing of the algae, so the volume where the algae live in the liquid, that they have a certain geometry that allows us to be very efficient, that the algae can produce a lot of oxygen and biomass with as little volume as possible. We have to provide lighting that's also for space as power efficient as possible. We need to make sure that our system is modular. So if the algae, for whatever reason, start dying in one of the photobioreactors, we don't have to kill the entire system, that we still have others working while we repair one of the systems. So there are many engineering aspects to consider when cultivating algae in space, which is not as necessary here on Earth. On Earth, if your algae system is contaminated, you can throw the algae away. You wait a month to have everything clean, and that's it. In space, we cannot just say, we'll wait for a month until I can cultivate algae again. So it comes with many challenges that make the design of the system much more complex and demanding for space.
So you already said you can eat them. How do they taste, or have you eaten them?
I've tried them. I usually take them to my lectures when I talk about algae to my students. And it's very interesting to see the faces of the students when they taste it. It's very salty. It really depends on your taste. I know a few people that actually like them. But most of the people just make a face. It's like, no. Salty taste. You can actually buy them pretty much everywhere. So there's, as a protein food supplement, chlorella or spirulina here in Germany in Reformhaus, but in general in supermarkets, you might find products with a very tiny part of algae, and that's the important part. They might not taste that good, or most of the people don't like them, but we wouldn't eat algae alone anyway. To have a balanced diet, we would need to include other food sources. So we can mix them, and then it's not that important any much how they taste, because, mixed with other things, they will taste good.
So, but mostly it is researched on microalgae as an oxygen supply, but also for food. How would you do that in the future? How would you use the microalgae for space food, I would say?
We've never gone that far. Of course, we always design our systems with the idea we extract the biomass from these reactors at some point and food will be produced. So we've always talked in general in our research or that's the next step, but never really fully done research on that. But it is done on Earth. I've seen in many products, there's pasta with chlorella. So it's the microalgae, it's a quite solid biomass that you obtain once you extract it from the reactor. And it can be then compressed in tabs or in powder form. And with that, it can be mixed with anything. So you shouldn't imagine a big bottle of algae and you with a spoon just eating that, or like a bottle full of green stuff. But it would then be mixed with other things. And it is it's very rich on protein. So from one side, it's very good to eat algae. But as I said before, not only algae, we need other sources of food for that. So it would be something that you would mix with other food sources you might either bring to your station or produce on your station. So might be combined with higher plants, with tomatoes grow on Mars or wherever we might see in the future on that direction.
What are the biggest challenges of growing them in space?
The biggest challenge that we have not looked into detail, I think, will also be scaling up the system. We are now working with small experiments. Our experiment on the ISS had about 1 liter microalgae suspension. And from our estimations, for a human, we would probably need 100 to 1,000 liters per person. So you can imagine we would not bring 1,000 of our small experiments with us. So scaling up the system is one of the challenges we have not really looked too much into detail yet. We always acknowledge it as a problem. And together with that, what I've already mentioned before, making sure that it works for long periods of time. You want your life support system to be working 100% of the time. And that's something we need to ensure that even when failures occur in the system, that we can overcome them and the algae can still continue functioning as we plan them to. So long-term stability of the system is also one of the big challenges still to be demonstrated.
How good can you simulate conditions of the that you have at the ISS on Earth?
That's a very good question. There are things we, in our case, we couldn't really test on Earth. You have to design with the knowledge that we have how things work in space, being the main difference microgravity. There are several ways here on Earth to, or different tools on how to test on microgravity. So you can do parabolic flights. There are rockets that also do their trajectory or drop towers. So there are several means of doing very short time experiments on microgravity. That's not enough for the microalgae because you don't cultivate algae for 20 seconds. You cultivate them for days to see a result. So there are things that we could only test here on Earth, being aware of the difference. What does gravity here on Earth? On gravity, the algae sediment. So we knew in our photobioreactor that we're testing on Earth, the same system that we send to space. The results that we obtain will surely be different because we know that algae are accumulating on the bottom part. We still created some movement inside to avoid that, but completely gravity is there. We cannot avoid it. So it was for us not possible to test fully all the aspects that you would have on the station. We did simulations, and again, we are aware of the difference and designed the systems accordingly to make sure that they would work on microgravity based on previous knowledge.
What would be then the challenges on taking them to another planet like Mars?
Mars and even the Moon are very interesting scenarios for us. So the surface of Mars and the surface of Moon for human spaceflight. Because having things in microgravity comes with a huge problem, not just for the life support systems, but in general. And that's the gas-liquid phase separation. On Earth, bubbles race on the liquid and you have your gas up and you have it naturally separated. The liquid stays on the bottom, the gas on the top. On microgravity, this doesn't happen and we have to find ways to separate the liquid and the gas. On the lunar surface and the Martian surface, we have gravity less, but we have gravity. And that's definitely enough for the bubbles to go up. They would go up at a different speed and the process might be a little bit different. But we have this natural separation of gas and liquid. And that makes the systems technically much more easy. And that applies also for the algae, because the algae are living on a liquid phase. They produce gas. So we definitely have this problem of liquid gas separation. So it is a very different concept when we think about Martian or lunar surface, how we would design the system technically, than microgravity. And it makes the work of an engineer, I would say, much easier to have a little gravity, even if it's less than what we have here on Earth.
Interesting.
If I'm correct informed, you also worked on Nauvoo. Can you maybe explain a little bit to that?
Nuva.
Nuva,
yeah.
Sorry.
Nuva was a very interesting project. It was more like a hobby project aside my work. I had the opportunity some years back to get in contact with some old friends, all interested in the design of habitats out of this planet, out of Earth. And we decided, let's work together. We have expertise in different fields. How nice would it be to get a project together? And you know how it is. You usually talk with your friends, we should do something. But if you don't have a goal, you don't do it. You keep talking about it every time you meet, but you don't really put your hands into work until you have a deadline or a certain specific goal. And in our case, shortly after we had this conversation, we should do something together. We saw that there was a competition from the Mars Society. They did it at least back then every year. And they asked a very specific question. That year was, how would it be a city on Mars for 1 million people? I have to say, when I first read it, it's like, 1 million people in Mars. Why would we need so many people? But okay, I'm the engineer. I'll solve from an engineering point of view how we could achieve that. And it was a very interesting project because we were a group of very different disciplines. There were a lot of engineers, aerospace like me, but also from other engineering disciplines. But we have a very strong team of architects. And that's a very good combination, having the engineers and the architects working together, because the architects make it look very nice and know how to do things on that direction. Engineers know how to design systems in space so the astronauts survive. If you don't have the people working together, the architects make something very nice, but probably deadly for the humans. And the engineers do something very safe, robust, but it looks awful. And no one would like to stay there for a couple of years. And of course, that has implications on your physical, mental state and performance. And it's not just about being happy about your house, but it has long-term implications. So having the possibility to work together, combining those aspects also with other scientists from physics, from chemistry. We were a really team combining different efforts. So that allows us to look into very good depth into the materials we have on Mars. How could we use them to build a city? Which materials do we even need to build a city? What does it mean to build a city? One thing is building a space station for 6 astronauts that are there for a couple of months and then come back. But building a permanent city. The cities have streets, they have schools, they have hospitals. How many hospitals do we need per person that we bring to Mars? So those are questions that maybe as aerospace engineer, I had zero idea about, but it was a very nice combination of different disciplines, everyone bringing a small piece of the puzzle. So working together, we came out only after 6 months. So it's not a project that goes into much depth considering the time, but that looked at many aspects that are important for a future mission to Mars. Maybe not necessarily for 1 million, but a couple of hundred is already a lot. So looking into that sense. And that was a very good exercise for us. I don't foresee this city to happen anytime soon in hundreds and hundreds of years, but it was a good exercise to see where are we today, which technologies do we have today, and where do we have to do more research, which is the direction we want to go, and which first steps slowly, one step after the other, but which direction should we go in our research to one day make that maybe possible.
A question comes then to my mind. Engineers always think about first the needs that everything that a human needs to go to space, but is there something that life support systems do to support the psychological health of us astronauts? especially for long-term missions?
That's a very important point, and that was not that relevant for the first human spaceflight missions that were very short. Like if you're going for a couple of hours, doesn't matter how comfortable you are with your surroundings. But of course, for long duration missions, that's very important. And that's actually a discipline called human factors. So I wouldn't put it inside the life support systems itself, but of course, it's two disciplines that, let's say, go together, and it's an important part for any human spaceflight mission. It has to consider the lighting that you have around you, the size of your room. If you have private spaces in your station, so you can say, okay, I need half an hour for myself. Can I physically separate myself for the rest? Do we ensure that there are common areas where people can spend time together? So there are many factors, as I said, starting with the lighting or the colors you choose or how you mark the different areas. So there are so many aspects to consider that ensure that long-term astronauts feel comfortable. And we have to keep in mind that comfortable, again, it's not only just for the sake of being comfortable, but also for the performance. When you feel happy with your surroundings, you'll probably be in a better state for work and perform better. So, that's definitely an important topic. Time scheduling, making sure there's enough free time, how communication occurs with ground. The list is huge.
Yes, I can assume. Yeah.
So in a time of climate change that we are right now, we talk a lot about future, but is there something that we can learn from life support systems? We call it a lot about reduce, reuse, and recycle. Is there something that we can learn from that?
Absolutely, yes. And I like this question. It's a question that always comes up, sometimes in a more provocative way, like why do we even need to go to Mars with all the problems we have here on Earth right now? And I like to answer with the research that we do here on Earth to go to space one day. It doesn't go thrown away to space and it doesn't stay here on Earth. We learn about developing technologies that allow us to live in a world that it's not made for us. Mars is definitely not the place for humans to live in. We can manage technically, surely, to create the environment for that, but it's not. And if we are able to think to that limit, how do we make the impossible possible? That brings us to come with ideas or with potential technologies that can also be used here on Earth. And the life support system is a very good example in the sense that we have to deal with, we could say, similar problems. What are the problems here on Earth? We have high levels of CO2. Well, in a station, if you don't do anything, in a small space, you'll quite easily come to high levels of CO2 for the CO2 that the astronauts exhale. So we are developing technologies on how to capture CO2 and how to make good use of this CO2. So those are technologies that maybe not one-to-one as we would use them on Mars, but the process of designing these technologies can surely help us on develop things here on Earth. The use of water, having the best use of water, recycling as much water as we can, we need to do that in the station. We also have problems here on Earth with some regions with scarce resources. Water is one of example, but of course food production is another one. We want to produce food in space with as little resources as possible. We want to produce exactly the amount of food that we require and not have food waste. We can learn from those things and we can try to be here on Earth a little bit more Martian, thinking about how we would be living on Mars. Let's try to apply some of those knowledge here. We don't have to live here in the extreme as we would on Mars, but we can surely learn a little bit from that and do things a little bit better.
Has there already been an example in the past that has already taken something from this research of life support systems to the life on Earth? And
there have been some examples of producing, thinking about microalgae, because that's where I read the most from my work reading, I would say. There have been some experiments, projects or pilot plans of producing food in regions with scarce resources, with little water, so that the population on those areas can have a high protein extra food source. So that has been done on that sense. And there's a lot of research on CO2 capture with microalgae as well, on how can we better use the microalgae to make sure that we reduce CO2 emissions locally at certain areas. There was a building with microalgae facades. It also didn't work as well as it should have, like our experiment. But yeah, there have been several ideas on that sense on how things that are part of the life support system could also be used here on Earth.
Okay, interesting.
And on which project are you working right now?
So I have to admit, I've been a year now here at the TUM. It still feels like yesterday, and we are going step by step, developing the professorship, which started from zero. And we're very happy that we're cultivating microalgae for the last couple of months. We started. I have a team with the postdoc expert on biotechnology, Sergio, and Lina, the postdoc PhD student, both working on the microalgae. So we're trying to establish first working systems in our lab with the goal to look for funding as next step for either or both an experiment to the ISS again, but already looking at the moon. There will be several flight opportunities over the next years to fly the payload to the lunar surface. So we are trying to focus a lot on that direction right now. But it's small steps, because we first need to have running systems in our lab where we say we're able to cultivate algae here, which at least from the space side has not been done before in the TUM. So that's one of the big projects we have started with more energy this last year. In parallel to that, regarding human spaceflight in general, we are organizing for the first time this summer here in Munich the Space Station Design Workshop, which is an activity where we put research and teaching together. We have a group of students being guided by professionals from the industry, from agencies, to design a space mission within a week. It's crazy. 1 week is not a lot of time, but we've done it many times. I've been doing it many times in Stuttgart, and now it's starting as a collaboration between the two universities. And I cannot tell what the exact mission design will be, because it's secret until the workshop starts. But if you're here around the end of August or in Ottobrunn, we'll be having the results presented with the first human spaceflight mission conceptual design happening here on the workshop in Munich. And then there's a third line I'll started working. It comes also from my heritage from Stuttgart time, of course. And that has to do with simulators. I don't know if you had the chance to be in Ottobrunn. We have a big simulator there. We have a Soyuz capsule, real size simulator, where we are currently doing some courses. So students also get to try to fly a little bit. But it's also meant for research purposes. We have a real simulator and a virtual reality one. And the goal for us is to measure performance and how performance of the astronauts or the candidates changing different factors. One factor is isolation. There are several studies of isolation. The ESA is planning currently 100 days isolation study where we would like to have a simulator to test the performance. But we can also change other parameters, like how do we show the information in an emergency case, and how do people react to this showing the information in different ways. So there's that would be the third line where we are starting even slower, but we already have some hardware there and some students working on student projects on the performance measurement and performance change for future astronauts.
Do you think VR could be like a key role for testing missions, like you said already?
It can help a lot. I mean, you cannot change everything or train everything as you would be in the station. Your feet are still in the floor. Of course, that you can also have systems to change that, but it can help a lot to test things in advance. And it's a field that it's growing not just for the aerospace sector, but in general. And here we are in discussions with the European Space Agency. They have also been working a lot on that for astronaut training in this last couple of years. So it's a lot happening. And of course, it's not the same to train in theory for something or actually seeing it and being able to do it with your own hands with VR. So it is definitely something that it's going to accompany us for the next years, for sure.
While doing our research for this podcast, we also read on this design workshop you're doing this August. We were asking ourselves, what would your approach be to a new generation space station like the ISS was? And what would be the core difference to the ISS?
It's hard to give a very specific answer to that. So we definitely need to continue doing research on microgravity because that allows us to learn a lot. So having a station like the ISS on low Earth orbit is surely a next step that after the ISS we would surely require. But we are also living in a time where things are changing from the public sector to the private industries. So we'll surely see very different stations in the future. Maybe not technically, because the technology might not change that much in the next 5 years. But the political scenario and the private sector scenario is changing a lot, and we'll see new things that we're not that used to. So in that sense, that we'll probably have private stations. We're starting to see that already with private astronauts flying to the station. So that will change a little bit in that sense. Technically, at low Earth orbit, I don't think it's going to be a dramatic change on the technology side. But I like to think on the steps that we're taking, again, step by step, slowly. That's, I think, the quite common thing for space, and especially for human spaceflight, where there's a high risk that we go stepwise solving the problems. We'll see soon humans going to Mars again. We'll see the first female landing on the moon, hopefully soon. So that poses new challenges on the design of the station. Radiation is a huge, major challenge to deal with in the coming years. We've mentioned Mars today already, so step by step, but we'll see many changes, rather looking into those scenarios more than thinking about the next station after the ISS in low Earth orbit.
And with all the political events going on right now, do you think an international cooperation like we had with ISS could happen again in the next 5 to 10 years with all the politics?
I hope so. I cannot make any promises, and we're all aware how difficult are getting here on Earth. But such a station, we need to cooperate because it's a huge project. But also because of the message it sends to the entire world, that we are able to cooperate together in such a hard and complicated endeavor. So I really hope it's possible. I don't want to be a pessimist, and even if I wish it, think that it's very hard, but it is right now complicated times. And we'll also see a change with the private sector and how that will play a role into that, and if we'll have private-public cooperations or how that will develop as well. So I think the future is very open in that sense, but I really think we should cooperate all together. But it's not just up to me. Yeah.
And we also talked a lot about like Mars and ISS already. Is there something different that you have to think about when you're designing the Lunar Gateway?
The Lunar Gateway in particular, yes, it's very different to the International Space Station in the sense that it's not crewed the entire time. The current plan, if that hasn't changed, it's to have crew 1 month per year. And that means that we will have the station empty for 11 months. It still needs to be ready for the next crew to come after these 11 months. And that's not something we have had these last 24 years with the ISS. There's always been humans have been there to repair things or to react if required. The gateway will have to be more autonomous, and we'll have to still make sure that it's a biddable volume for the humans to come when the time comes. So that is, I would say, one of the big differences for me, which makes it less interesting from the life support system side, because only having humans 1 month every year, it's a very different scenario. But of course, it's an amazing project that will come with new technology advancements because of the different conditions of the station. Yes.
As you already said, repairing must be more autonomous. Do you think robots will play a crucial role there?
Definitely. And talking about the moon is one thing, but we can even go one step farther and think about Mars. Communication with Mars, depending where the planets are, Earth and Mars respectively, we might have a 20 minutes communication delay each way. So we cannot expect people from Earth to deal with the problems and have communication when there's problem. The mission will have to be autonomous. And of course, if it's a crewed mission, humans will be there and will be able to react. But having robotic support and that's something that's also taking a lot of speed these last years. And there have been several robotic missions and interaction with robots also in the space, International Space Station. There have been experiments like Simon, where there's a robot interacting with the astronauts. So we'll see that more and more. Yes, that's definitely a thing.
You mentioned the distance of being a problem for maintaining life support systems or repairing something like that. But what are other challenges of maintaining life support system in harsh environments like Mars?
I have to admit that when we think about the life support system, we tend to think of it being inside a habitat. So I have my right conditions already. I have a structure that supports my pressure difference with the outside. I don't see that as my problem to solve. I assume there's already that is provided, and I make sure that the air that it's inside is at the right conditions. There are still, however, some challenges that change a little bit depending on the mission scenario. If we talk about the lunar surface, Martian surface, we have gravity, which is good. But then we also have the lunar regolith, for example, or on Mars, sandstorms that can create many problems. The lunar regolith is very harsh on its edges and can be very abrasive for the materials. And if it gets inside the station and ends up in the lungs of the astronauts, can also be very dangerous for the humans. On Mars, the sandstorms can create huge problems, for example, on my solar panels. So if I don't have solar panels, maybe I don't have light for my algae. So there are specific challenges for the specific destinations. And I would say those are two of the biggest ones beyond radiation, as mentioned already many times. Radiation is a key element for human spaceflight, unfortunately.
Okay.
I think now it's a good time to do a tier list. We're going to say 5 space events, and you have to rank them from 1 to 5. 1 the best, 5 the worst. The first one would be the first lunar landing.
Oh, okay. Have to be wise. I would say let's put it 3.
Okay, second is the person Yuri Gagarin's. The first
flight.
Yes.
Oh, God. That's already hard at this stage. For the importance of being the first human spaceflight, let's put it 2.
The next one would be the first sandwich in space.
5. I'm happy the astronauts were happy about it, but yeah.
Okay, then the first recovery of a booster.
Oh, that's a really good one. That was a really big step, but not knowing what comes next, I'll put that as a 4.
And the last one would be first crewed Mars landing.
Perfect.
Okay. That sounds good. That sounds good.
As we mentioned in the game, recovering a booster is changing, I think, a lot. Also maybe for life support systems, because we can bring higher payloads to the orbits. What does it change for life support systems?
It actually changes a lot how we think, because that has allowed the cost of each kilogram that we send to space to go down. And our argument for a long time, and it's still valid, but we have to be more and more cautious about it. It's we need to recycle absolutely everything because sending things to space is expensive. And now we come to the prices going down. So the question is, how expensive is too much? So it opens a possibility to being able to bring more things from Earth up to space. But I still see a limitation on that. It's not only about the money, it's about of the fact of knowing that you're producing your own food, that seeing your own food growing. So there are many more advantages than just the money. But it's true that for many years there has been one statement like, yeah, we have to recycle because it's expensive. And that is changing. If we think about missions to Mars, we're again at a lower level than sending things to the ISS. So I would say that the expensive, it's still valid at this stage, but who knows what's going to happen technically these next years and what we will see, who will land first on Mars with a big rocket. We'll see how things evolve on that sense. So, of course, it has a direct impact on the cost of sending things, but we have to also consider the psychological value of producing food in situ as an example of why, regardless of the cost, it might be important to do research on that direction.
Okay, speaking of that, I wanted to ask you if you have or can share your opinion of SpaceX Starship, which is probably the most popular project right now, speaking of Mars missions.
I would say we'll see what happens in the next years. I'll not express any strong opinion for or against it. In general, not specifically for that, but in general, what SpaceX is achieving is amazing. I mean, the landing of the booster, who would have thought that to be possible not that long ago? Having now crew to the ISS being sent by SpaceX in a regular basis, that's also an amazing step. And I'm sure if they want to land the big rocket on Mars, they will. They have proof that they promise and they deliver. How exactly that would look like at the end, how much crew would be sitting in that mission to Mars, and all those things are something that maybe still not discussed in depth enough. But I think we'll see that happening, and I'm looking forward to that because that pushes the industry in that direction. But I'd like to hear more about details before having a strong opinion on that.
Okay, all right.
Did you watch the last Starship launch?
Yeah, I tend to watch almost everything that it's possible, unless it's in a very unreasonable time of the day. With my colleagues at work, we tend to do that when there's some important event. We tend to follow online the launches. Yeah.
Okay, so we're coming to the end of our podcast, and for the last few questions, we wanted to ask you what advice you would give for young engineers and students who are aspired to work in your field of life support systems.
I think in general, human spaceflight is a great field to work on. I have to experience over these last years how inspiring it is. For me, of course, I go to work every day with a smile on my face because the work we do is amazing. But also to the general public, it's something you can really reach the next generations, not the ones you're mentioning, but the younger ones to come. It's amazing to go to schools and explain them how we are managing to design technologies to keep astronauts alive in space with our microalgae or with other technologies. So it is a field where it's very easy to be passionate about. I mean, everyone has their own passions. I'm sure there's people that love Formula One cars and are very passionate about it. But I think space has really something special, and human spaceflight even more. So it's from the engineering point of view, there are enough challenges to solve. So that's out of question. But it comes for me with this extra motivation of then seeing the astronauts up there actually doing your experiment or trying your technology and knowing that in a very small part, you're contributing to that being possible.
Yes, I see that. And especially as a woman in this sector, is there something you do or you see is do a project that is getting the attention from more women to work in this field?
I think that the topic woman in aerospace in general is problematic. We're very few working, and depending at which levels you go, it's even less. I think this is changing slowly, and I participate in several initiatives to give visibility to women working in this sector. From Women in Aerospace Europe, we've, for example, tried to organize talks where women working on the area show what they do, because there are plenty of women doing interesting things in the sector. And I think it's about giving visibility to them. Sometimes maybe we're more shy. I don't think I am, but in general, we don't dare to show what we do, or we don't think it's as amazing as it actually is. So trying to give a push into that direction. For me, it's the right step. I wouldn't push any percentages of so many women have to be working in this field, but let's just show the next generations how many amazing things are happening done by women, also by men. But let's also give the voice to the women that are working in the sector so they have examples for the future.
I think that's a pretty good ending. Thank you very much for coming today.
Thank you for having me here today. It's been a pleasure.
Thank you for listening. Please subscribe and like the video or the podcast, and buckle up for the next episodes.